Good morning. I hope that you had a lovely weekend. I hope that your morning wake up was not as rough as it was at our house. I know with the time change, it kind of messed with everybody's.
I was going to use the time change. It should not come to school today.
Yeah, how'd that go for you? You're here, so I'm glad for that.
It was only because my good conscience came out.
You're a good kid. I love it. I love it. So I'm glad that you're all here. It's nice to see you this morning. It is the last Monday before spring break, so there's that, and that's a great thing. We've got a bunch of stuff to do today, so we're going to jump in just a second. We've got a capture question to start off. We're going to work on some things, talking today about the cause of all of this climate change that's been happening. That's an important question as a scientist, right? It's not just that it's happening, but why it's happening. So that's going to happen. I want to give you a heads up that we do have a quiz tomorrow, a 9 or 10 point quiz. So kind of like not one of those little itty bitty quizzes and not like a big, huge test, but kind of something in the middle. Okay. So it will be something that you will absolutely want to study for a little bit so that you know what's going on and you're ready to go with it. But I wanted to let you know that it was there. I am also going to let you know that I have not yet posted, but I will post a video with some greenhouse gas notes. I know some people like to have that kind of like one more direct instruction of what the what the content is. This comes from the lab that we did. You guys watched some videos and took some notes, and this is kind of the next piece to that. Okay? Right now, we're going to jump in with the capture question. While we're doing that, on Friday, you may remember that we did not quite get that web quest done because the tiny URLs were being all really goofy. I sent you an email with the new links, like the big links for them. So hopefully at this point you have your web quest done. I hope that you also have completed the greenhouse gas lab with the graph on the front and then the questions that were answered from video on the back. Okay, I am looking for both of those sheets, so please pull both of those out so that I can check them, as well as your capture question.
What?
Because here it comes. Last week we spent a lot of time with this graph. Oops, you can't see it yet. Last week we spent a lot of time with this graph. Hopefully this looks familiar to you. If it does not, then you'll want to go back and watch some of those videos so that you can be reminded what was going on there. Today, friends, today we're going to zoom in on this part right up here. Okay? So the question comes from that. It requires a little bit of background, so I just want to tell you what's going on here. In this graph, we're graphing carbon dioxide concentration. So the same thing that we were graphing in the last graph over time, but this is direct evidence. This is direct data. You remember with the other one, when we were talking 400,000 years ago, we're talking ice core data, right? That's indirect evidence. This is direct evidence. They actually took samples of the atmosphere from 1955 to 2015, okay, and measured carbon dioxide levels throughout time. This is at a observatory in Mauna, Hawaii, and so they graphed it over time. Your task for this capture question is, given that, what conclusions can you draw from this graph? Okay, I want you to be specific, and you notice that it says conclusions, meaning that you should probably have more than one, like 2 or 3, something like that. Okay, so take a look at that. You've pulled out those other sheets so that I can take a look at them as well. Okay, okay, friends. So hopefully you've come up with some really great observations that are going to get us through here. Here we go. So the concentration of CO2 in the atmosphere measured without interruption. So this is not like we're just cutting little pieces. We're like looking at it over time. Question or conclusion that you've drawn?
Observation.
Observation, do it.
So it looks like that they're zigzagging.
It does look like they're zigzagging. I love the fact that you said that. Yeah. So the data zigzags, is that a technical term? I'm going to call it a technical term. Good observation. Is it about zigzagging or no? I want to do just zigzagging first, and then we'll come back. Is that okay? But can anybody come up with a reason that might be happening?
Wasn't it like global heating or something like that?
Well, let's look at this, though. This is from 1955 to 2015.
I think that's
So, yeah, I would too, right? And the reason that I like this graph and the reason I like this as compared to the other one, I mean, it's a really good question, and I'm going to come right over here in just a second, but I want to look at this. This one zigzags too, doesn't it?
Wait, does it have to do with
But,
winter?
what?
Does it have to do with like winter and summer?
Yeah, it might. Okay, so let's back up for a second. This one goes from 400,000 years to today, right?
Yeah.
400,000 years ago, what was happening then?
ice.
We talked about this at the end of class yesterday on Friday. Come on, friends.
Oh, humans.
Humans were there, weren't they? But was it like Homo sapiens?
No, it was the Nari.
This is like pre-Neanderthals, right?
Yeah.
These are people that are finally using a spear, right? Like that's what we're talking about. We're talking about cave-dwelling people. We're talking a long time ago, right? I think if I'm remembering correctly from our conversation that speech started over here, right? So we're talking not even like speaking situation then, right? So there is a zigzag, but I want to look at this zigzag that goes up and down versus the zigzag that we have here. There are some things that are similar and some things that are different, aren't there? What do you see that's similar or different?
That one's more consistently zigzagging. The other one is kind of just like drops. And then, like after a while, it like this is actually like very it's a pattern.
It's a regular pattern. Yep. Is it more frequent or less frequent than the last one? More frequent.
It continuously goes up.
Yeah. So it's a regular pattern. It's more frequent, but the values keep increasing, don't they? Whereas and this is really important, this is the science we're talking about, friends. This is the stuff that I want you to be able to understand and see. So in this one, the zigzags don't go above like 300, right? And they don't go below about 180. So they always go up and down and up and down and up and down with the same kind of maximum and the same kind of minimum. Whereas in this one over here, they do go up and down, up and down, up and down, but the maximum keeps getting maximumer, right? And even the minimums keep getting higher and higher. So that's important to notice. We'll put that down here. So they're more frequent, but the overall, we'll say values always increasing. Is that an okay way to say that?
Yeah.
Jackson, I feel like you want to say something back there.
Does it have to do with like during winter we use more cars?
It does have to do with seasons. Connor, I feel really bad because you had your hand up a minute ago and I totally dropped that ball. The winter and summer thing. So it has to do with seasons. It's not actually because that we use more heat in the winter though, okay? It actually has to do with, let's think about the carbon cycle. Do you remember that from forever ago where we had people running around with carbon?
Yeah.
Remember? There was one kind of area that liked to take in carbon, and it used the carbon. Do you remember what uses carbon? I heard a lot of things there. So water takes in carbon, but it doesn't really use it. There's something that uses it to grow. Let me put it that way. What are you saying? The trees, the plants. Trees and plants take in carbon dioxide through what process, friends?
Oh, there's no trees and plants in this.
Photosynthesis. Whoa, what? That light bulb just happened there. Tell us, share the brightness.
There's not as much trees and plants in the winter, you know?
Yeah, well, the trees are still there.
Yeah, but it's not as
But they're,
green, you know?
yeah, they're not doing the photosynthesis business, right? That's the big deal.
It's all white.
What were you going to say, Chris? Were you going to add to that? No? That's it. That's a big deal. During the winter, in fact, it's right. It's written down here even. Look at that. So this guy, Charles David Keeling, he was actually a graduate student. He's probably like 28 or something when he started this. He's like, let's collect CO2 data. Let's find out what happens. He showed that CO2 underwent regular seasonal cycles because of the growth and decay of plants. During the summer, the plants are taking in a lot of carbon dioxide, right? Because they're doing that photosynthesis stuff.
Yeah.
And so that means that the carbon in the atmosphere is going to go where? The carbon dioxide levels in the atmosphere, are they going to go up or down? What is it? They're going to go down because the plants are taking in all that carbon dioxide. During the winter, very little photosynthesis happening. That means that the carbon dioxide levels are going to go up, right? And then you also remember that when the leaves fall and they break down, then they're going to release carbon dioxide back into the atmosphere. Does that make sense? Yeah. It all comes together. It's like a big cycle and stuff. Yeah. All right, that's a big deal. What else you got? The zigzags absolutely happen. There are a couple other other observations that I would like for you to see. And as much as I love Jackson, I don't want him to tell us everything. So I want to share the fun. Do you need another minute to talk to your table mates to come up with some other observations? You've told me a bunch of stuff too. I want to share the fun.
But I have.
But you have one that you really want to share? What? Oh my gosh. All right.
It goes continuously up.
You got to be careful about your words though. Is it continuously up from here to here?
Dude, you told me that.
It goes down. Can't trust him, you know what I'm saying?
Not trusting them.
No trusting there. It does, the values do regularly go up, don't they? Yes. Overall, are we showing kindness back there? Because it does not sound like it. That's good, but I want you to also live that kindness, right? Yes. If you don't have this stuff written in red down on your paper, it doesn't have to be written in red, but if you don't have this stuff written down, I would write it down. The CO2 values also do generally increase and do they increase at a constant rate? So they keep going up and up and up. A constant rate would mean that it goes in a straight line. So they don't increase at a constant rate. Do you see what I'm saying here? If I draw a straight line here, it's just going to keep going like this. So the rate keeps doing what? The rate keeps going up. So the CO2 values generally increase at an increasing rate. That's important. There's one more observation that I want you to make. And in order to do it, you may need to get the brown paper that has that graph on it out. Would you get that out real quick so you can compare values to the values here? Pull that piece of paper out that we had from last time. Pull that graph out and take a look at it. And take a look at this graph and see how the values compare. See how the numbers on the y-axis compare to these numbers. What do you see? What do you observe? Talk to your table mates.
With the line right from the low.
Yeah, that's
Hi.
This one should actually end that
Yeah.
What kind of observations did you make, Hayden? What'd you guys come up with?
Go ahead.
the graphic
Uh-huh.
starts with this one ends.
It does. Like, are you talking about time-wise or are you talking about CO2-wise? Time-wise, it does. You're right. Good call. Good observation. So he says that the graph on the board, this one here, starts where the other one ends, right? Because this one ends at like 1950. So does that mean that this really should go like this? Like the graph we had? Does? Why no?
Because, like, the graph,
The other graph?
yeah, it's like basically really like spread out so you can actually see the information.
Yeah. This time frame here, this goes from 1955 to 2015, right? So that's what, 60 years? Whereas this one here, this is in thousands of years. This is 50,000 years, right? That's like a bunch of zeros different. So it shouldn't do this. It should go straight up. So that's absolutely true. What else do you notice?
This one ends at 300, like that's the highest it goes, and the other one starts at 300.
Right. That's a huge deal. I want you to write that down in your capture question. We said that we have the highest historical levels at about 300 prior to when people got involved, right? Not that people were here, but people didn't really get involved with the problem until here, right? Until the 1950s. That's when all this problem started, okay? 300 isn't even on this graph. It's like down here, okay? This is the highest historical levels. All of this stuff is above, right? And like a lot above the historical values. Let me show you one more graph real quick. So they took this data and what they know and they superimposed it onto the graph that we looked at last week. That's what they think is going to happen. The y-axis has changed a lot. Here's 300, friends. But look what happens before that.
Yeah, it goes.
Why? Any idea why?
We all die.
We use everything up. So it's funny because we were looking at this as an earth science staff a little bit ago. We're like, oh, it goes down. That's great. Here's the problem. Before that happens, we have screwed things up so much that there is no going back. You with me there? We have screwed things up so much that this normal atmosphere that we are used to will no longer be that way. Okay? So yes, it does look like it goes down here, but that's because we've used up all of the fossil fuels on the earth, in the earth. And we have now, so historical maximum was 300. We get up to 1,600. With me there? It's a lot more. That's more than 5 times the amount of carbon dioxide. Yeah.
How, what year do they think that's gonna happen?
I don't know if I wrote that down in here or not. I don't have it in here, but it's, a few hundred years from now. Not a long time. Not a long time. I want to write one more thing down before we move on. Yeah, that's true. And so life is good then? Sweet. Who cares? I mean, not gonna lie, and I like you a lot, but that's a pretty darn selfish way to look at the world, right? And I'm not saying that it's just him, because I'm guessing that others of you are thinking the same thing. But just wait until you have children. And then you're like, oh my gosh, we're totally cheesing them, right? I guess. And we're going to read about that in just a minute. Before we do that, I want to write one thing down. Shh. Because I want to make sure that you know it so that you're ready for it when you see it tomorrow. Why is carbon dioxide so bad? What does it do? It heats up the planet. How does it do that? So it heats the atmosphere by trapping radiation that would otherwise leave, right? And what other effects does that have? The warmer the air is, what happens to the water in the oceans? And it gets warmer, and then what happens more? More evaporation, yeah. And then more evaporation means more what in the air? Water vapor. And what does water vapor do? It heats up the atmosphere. You with me there? So we got lots of water vapor in the air. We got lots of heat or lots of carbon dioxide in the air. It's all trapping that radiation, causing more evaporation. And it's a big old cycle, okay? More evaporation means more greenhouse gases. And what was the most common greenhouse gas, by the way?
Water vapor.
Water vapor. Which means that it heats the atmosphere, traps the radiation, more evaporation, more greenhouse gases and water vapor, et cetera, right? It's an ugly cycle. It's absolutely an ugly cycle. Today we're going to figure out why this all happens. We're going to spend some time looking at the Industrial Revolution, okay? What I would like for you to do right now, you can put your brown sheets, your green sheets, your blue sheets, all that stuff from before away. I would strongly recommend, though, friends, that you spend some time today during a study hall, tonight after practice, tonight after babysitting, tonight after whatever it is that you do, studying so that you're ready for this quiz. Yes, there will be a retake. Yes, the retake will be harder. Okay? So better to get it done now. Send one person from your table up to get a yellow sheet and a green sheet for each person, please. And if you happen to be sitting, then you can start reading. Yeah, you may quickly.
Wait, hold up. Was everybody before Industrial Revolution anti-vax? Jackson did that.
Child.
I have some serious questions.
All right. So friends, I am hoping that this activity will make reading articles a little bit more engaging. Yes, quickly. Okay? If we're going to do this, though, I need you to listen. That means stop talking. We're going to count off in just a moment. You're going to be assigned certain sections of an article to read and to understand, and then we'll mix up so you can share out your information. Okay? Before we do that, though, I'm going to give you just a minute to read this first page. This is the front of the green sheet. Go ahead and do that right now. Some of you are done, some of you aren't quite done, and I apologize if you're not quite there, but We're going to just keep an eye on the clock and keep moving. Okay. So, on Canvas, there is an article. It's actually 2 articles that are put together. Okay. And there are 7 kind of big sections. I'm going to divide you into 7 groups, and you're going to read the section that you're assigned. And then as you read it, you and your partners will talk about the 3 big things. So the first one is the main idea. What is the big takeaway from that section? The second thing is the most interesting fact. What did you learn? What was like the kind of surprising thing that you found? And then number 3, tell me whether based on that reading, the Industrial Revolution seems like it was a positive thing or a negative thing. Okay. And this is important here, so I want to make sure it is included. The other part of that question is why. Okay. So we're going to count off by 7s, and then I will assign you section. So we're going to start with Jackson. You're going to be number 4, 5, 6, 7, 8 is going to be right there. Or it's going to be 1 is going to be right there. You're going to be 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5. Sound good? Okay. On the yellow sheet, on the front of it, take a look here. 1s are going to be in charge of, you're actually in charge of 2 little sections. So go ahead, if you're a 1, you're going to mark this. Industrial Revolution Introduction and Era of Sustainability. 2s are going to be in charge of the Industrial Revolution and population growth. 3s are going to be in charge of awakening to the implications. On the back, 4s are in charge of 2 short sections, continuing the ecological impact introduction, and what if? 5s are in charge of ensuing impacts. 6 is in charge of beyond energy. 7 is in charge of the rest. Okay? You can find this article on Canvas. Right down here at the bottom, it says Industrial Revolution Articles. Okay? If you would rather have a hard copy, I've got like 5 hard copies. You can borrow one. Okay? So we're going to put 1s right here. 2s are going to be at that back table. 3s right here in the middle. 4s, 5s, we'll say 6s and 7s. Okay? Find your person or people. You've got about 10 minutes to read. 1, 2, I was going to put 3s right here.
Hey, what are you?
I'm doing
What are you?
Hold on just a second, sorry.